Never mind lah, I give up this time. Bila I buat seorang okay pula. You can try this sometimes. So memang adjust button ni dia kadang-kadang dia ada issue sikit. So but we already know this one is if we were to do it at 34.35 tadi. Okay. No. Let's delete this one. Yes. 34. 0.999 lebih kurang lah. Okay, I think 34.38. Ini after I buat hari tu my iteration. Sama, dapat 0.999. Never mind. 99.9% is good enough. Or close to 1. Okay, now let's proceed lah. Sorry lah, I tak dapat nak tunjuk this one. So, now, let's proceed. A mixture of ammonia and water at 146. Okay, ni kita dah buat benda ni. The second part, we want 0.999. Basically, we have achieved that 0.999. That's great. And second part, the vapor stream from V100. Okay, this one. Okay, now what happened? Kenapa jadi macam ni? Just to show you the trick. Hari tu I copy tau. I copy the whole stream because I want to add heat exchanger dekat sini. So now we are going to do the heat exchanger. So you can actually copy this. Just copy everything. Right click. Where is it? Copy. Then you bring it down. You can always copy it here. Sebab I'm too lazy to do it in a new page. Okay. So you can have a copy. It will copy everything lah. So tapi please note that the stream number already, it all has changed. Now just delete this one back. Okay, I want to delete this. Okay, let's work on this so that we can get something like this. So now this one, at the end of the day, kalau you tengok, I want everything, this is the ammonia with product purity is of 99.9%. Kecil sangat ke you all? Okay, now. This is ammonia with product purity of 99.9%. So this one from stream yang vapor phase tadi dekat flash drum. So yang that one tadi separated, that is actually a flash drum. So kalau you tengok the composition is what we want. And then everything is in the vapor phase. So now, when we want to store it, we want to store it in a liquid form. Okay, so the condition is liquid and the composition still remain as 99.9%. So let's change the basis as fraction. 0.9 samalah mass sebab dia very small water content kat dalam tu. So what we want to do is that we are going to apply a heat exchanger and by cooling it down by using a refrigerant. And this one, if you see, the flash drum is not able to fully separate the ammonia from water. So in this case, kita ada, kalau you tengok dekat composition, you still have about 69% of ammonia. So the flash drum in a way is not able to fully separate it. So you can change this to a distillation column later on if you are not able to do it. But if you want some of the product to be for some other further process, you only want to have some that is fully separated, this is already fine. Because in this case, I just want to show you the function of, your function of a flash drum. So this is a flash drum. Okay, now, another important aspect, if you are trying to separate two component, okay, two component in a flash drum, okay, it is very important for you to make this one at saturation condition. So this is a saturation condition. Okay, but if you are trying to separate three components, it doesn't work. The same goes to distillation column. Okay, sekarang kenapa ya we want to reduce it to saturation, because this is a point, this is the temperature and the pressure where it is about to boil. So when it goes into the flash drum, the change of pressure, because of the pressure drop kan, the change of pressure, as the pressure reduce, the more volatile component will evaporate. So in this case, it's ammonia. Okay, but we cannot actually, when you dah cuba tukar-tukar the temperature in here, macam kita buat tadi kan, the temperature of your process condition, but you still cannot get the full separation of ammonia, you know it's time not to use flash drum, but to use other type of separation process, such as distillation column. So when you design the whole plant, you have to use this kind of, you must have this kind of knowledge. You can either skill, okay, to determine what are the best equipment, separation equipment to be used. The flash drum is one of the separation equipment lah yang kita biasa guna. Okay, so now what we want to do is we want to liquefy the ammonia in here. Okay, what we want to do, let's work with this one. Okay, now let's find our heat exchanger. So our heat exchanger is here. So this is our heat exchanger. We just bring it there. Okay, you bring another stream. Then we have another stream coming in that is at the shell side. Okay, now we are going to use refrigerant. So we have to specify refrigerant ni. Okay, now the refrigerant is going to use, kalau you baca dekat soalan, the heat exchanger setting is a simple weighted type, pressure drop shell side 10 kPa, tube side 35 kPa. The heat exchanger 102 use refrigerant 114 as cooling medium. You may use Pang Robinson for flip package for refrigerant 114. Okay, now I've given you the spec for refrigerant 114. So we don't mix the refrigerant punya line ni dengan yang the main line ni. Okay, so what you have to do, you have to go back to properties, and then you have to select component. Okay, now the component in here is, I already have the component ni, tapi let's just add them. Just tak nak bagi you confused. Sebab tadi kan kita share the page kan dengan yang atas tu. So let's choose refrigerant 114. You add it there, and then you go to flip package. Then for flip package, SME yang mana ni? Ya. SME is okay. Refrigerant. Ya. This is water. This ammonia water. I thought we just added a new one. This is the one, basic sticker. Sekejap let me check. You got confused ni because ada banyak page kat sini, ada banyak. Oh, it's already in basis 3. So let's create, I ingat tadi, let's create a new component 4. Okay. Oh, this is a flip package. Okay, never mind. So let's pilih Pang Robinson, okay, to be attached with component 4. Yang a component list 4, okay. So now component list 4, that's right. Okay, now we are working with basis number 5. Now let's go to properties, solid simulation. If we go down, okay, now we are about to simulate heat exchanger. So the main process usually would be at a tube side. The shell side would be the refrigerant. So the tube side is 4.2, okay, and then coming up from the top side outlet would be 7, okay. The shell side would be 8, and the shell side out will be 10, okay. Now this one is refrigerant kan, so we are working with basis 5 tadi kan, basis 5. So change the shell side to basis 5, means that your tube side will be working with basis 1. Basis 1 tadi, it contains the component of ammonia and water, Peng Robinson. But for shell side, we choose refrigerant and we choose basis 5. Okay, and now we have to specify the composition for 8 ni, because it's refrigerant kan. The composition here is only refrigerant 114. So let's put this one as 1 because that's the only komponen yang ada dekat situ. Does not really matter. And then we have to specify the condition. The refrigerant, the inlet to refrigerant is minus 80 degrees Celsius because it is a refrigerant. And the pressure is 5 bar, 500 kPa. And the flow rate is 3000 kilomole per hour. Okay, so nampak kat sini dia ada fluid package basis 5. So we are okay with that. Now, set the T out of the tube side to be 10 degrees Celsius. So we want it to be 10 degrees Celsius because we want to liquefy kan this one. So it is wise if you check the saturated temperature of stream 6 before deciding the stop temperature of liquid product of ammonia. So kalau you tengok dekat sini now we want to store this one in liquid phase. So we do not know what's the temperature going to be. Okay. Oh, now before that, we have to put in the pressure inside the heat exchanger. So let's bring it in again. Okay. The heat exchanger. You go to parameter. Okay. Now, you can find the pressure drop of the shell side and the tube side over here. Okay, and then the heat exchanger model that we are going to use is a simple weighted model because I really like this model. It's easy to converge. Now, the shell side, the pressure drop is 10 kPa. 10 kPa, and then the tube side, let's make it 35 kPa. Right, this is underspecified. Kenapa? Okay, now it becomes underspecified because we have not decided what's the temperature of the tube side yang kat luar ni. So again, we want to make it liquefy, jadi kita tak nak gas because the pressure here is 8 bar. Is it? Apa the pressures ni? Alright, okay, now the pressure 8.5, so this one it become 8 bar lah. So we don't want to do the gas work dekat N7 ni. So what we do is that kita letak dekat, we put 0 as saturated temperature. So everything will be liquefied if the temperature is 18.17, but this is at saturated condition. So we do not want to set the temperature is at 18.17. Remember, this one is to be stored in the tank before you send it to your client. So we do not want the change of pressure will evaporate material ni. So you have to set the temperature lower than the saturation temperature. So in this case, let's choose, just choose, ikut suka you nak choose berapa, just use your common sense. So let's choose 10 degrees Celsius. So it's already in liquid phase, okay, and this is converge. So let's complete this because this is to be distributed to your suppliers. Now the pressure here is at 80 bar, so we want to reduce the pressure because the pressure is 8 bar. We want to reduce the pressure. There's no point for you to store it at a high pressure because it will only increase you punya design of your tank and the pipeline along the line tu. So what we want to do, never mind. So let's install the valve because we want to reduce the pressure. It's there. Okay. And after that, let's choose a tank so that you can, this is a tank, so that you can actually install it. Okay, you must have a vapor out lah because kita takut if any case it will evaporate. So just let it vapor in your tank, that's tu tak apa. But then the molar flow is 0. So now you have 7 in here. So that's 13. Okay, unknown delta P. Right. So what you have to do is just check it. So the pressure drop. Say if for example you want to reduce it to 3 bar. Okay, now you have to keep it temperature as -8 and the vapor is dia vaporize sikit. So you don't want it to be at 3 bar. I pun tak tahu kenapa I buat 3 bar. Now still vaporize. So if you want to maintain the temperature at 10 okay, now tadi dia punya temperature at 10 kan. So if you want to reduce the pressure, you have to reduce the temperature. Okay, because you tengok this one is already vaporized. So if you want to reduce the pressure, say for example 300 kilopascal, so this one will vaporize and you will have a loss of ammonia in there. So you just want to keep it at 8 bar. So and then so that you can keep the temperature in here at 10 apa ni dekat 10 degrees Celsius, but you still have to supply heat, supply coolant to the tank. Unless if you want to store it at higher pressure, so you can actually store it at probably at 25 degrees Celsius so that nothing will be evaporated. So you have to make some evaluation, economic evaluation. When you work in industry apa, you have to make an evaluation which one is worth it for you to increase the pressure to install the compressor over there to increase the pressure so that you can store the temperature at you can store your liquid at 25, or you store it at 8 bar, meaning that your design semua has to be at 8 bar, no compressors, but you going to use utility to heat this one up to 10 degrees Celsius all the way. Okay, so in this case, let's lose this valve because there's no point for you to reduce your pressure, but then utility you bertambah dekat sini. Might as well you just do it once and for all. The design is for 10 bar. Sorry, the design is for 8 bar and 10 degrees Celsius. Macam ni So you can actually connect this to your tank. So that's your 7. So that's 12. And that's 11. Okay, by right you kena masukkan the energy dekat sini. You have to put in the energy to keep it. You have to extract the energy lah because you want to keep it at 10. But then because we say that, okay, in here. But then once you put in energy, you have to put in dekat sini lah. Okay, your temperature. So you want to keep it at 10 degrees Celsius. So kalau you tengok this one is 0 actually. But in real life, if your ambient is 35 degrees Celsius macam Malaysia, definitely you have to have a coolant dekat sini. Depends on where you do your operation. Tapi you still need this. Okay, if you are running it at a 4-season country, when it's winter, you have to put in heater. Or you can reduce the pressure somewhere lah, I don't know. So if it's a hot country macam Malaysia, constantly 35 degrees Celsius, definitely you have to put in utility to keep the temperature in the tank at 10. Unfortunately, Hysys dia tak baca the ambient temperature, so you have to use your weights lah. So kalau if you want to delete EQ 100, this one will give you 10 degrees Celsius, but when you want to do the individual design of your tank, of course you have to put in the utility in here, depending on which country you are running your plant. Okay? Senyap je rasa cakap seorang kat komputer ni. Okay?
Okay, doktor.
Ada soalan apa-apa tak sebelum I proceed to the next one? No? Okay, now let's do this. This one is in liquid form. We want to reduce the soalan kata in order for this to be separated, soalan kata kan, use heat exchanger as a steam as a heating medium because we want to vaporize this one again. This one has been separated and we want to vaporize this again. So we are going to use the heat exchanger, and this time we are going to use steam as heating medium. So if you can remember my class, my lecture last week, so if you were to use steam, the best fluid package to be used for steam is ASME steam fluid package, and we only use water. So in this case, let's find our heat exchanger again. I couldn't find it from here. Where is it? Where is it? So much easier to... Here you go. Okay. Now, to add this one, add another stream, add another stream. We are okay. Now we go to properties. Component list. We add another list. That's water. Sebab steam is from water, okay? So we add. So that is component list number 5. Then we go to fluid package. We add the fluid package that is basis number 6 attached to component list number 5. So we choose ASME steam. Now we go to simulation. Again, we plug in the value. Okay, the tube side inlet. So this is the tube, that's the shell. So the tube is 5.2. The tube outlet is 13. The shell side is 14. And the shell side outlet is 15. Right. And then we go to parameter. We want to choose again the simple weighted type of heat exchanger. The shell side, again, we are going to use 10 kPa. And the tube side would be at 35 kPa. Okay. Okay, we are okay in here. So now we have to put in the composition of your shell side. Oh, okay, hang on before that. So we have to choose the basis in here. Okay. We go to connections. In here, we choose the basis 6. So now your tube side guna 6. Your shell side guna basis 6. Your tube side guna basis 1. So in here, we put in the composition. And then we only have water in there. We have to tekan enter. We are okay. And we go to conditions. So the temperature is 200 degrees Celsius because we are talking about steam. 200 degrees Celsius. And the pressure is at 5 bar. I think this is medium pressure. Enter. And the mass flow rate is 2,500 kilomole. 2,500 kilomole. So we are going to tell the heat exchanger what will be the T out that we want. Okay. So now we want it to be vaporized. We want to condense it. Okay. So when we want to condense it, we want to choose a temperature higher than the dew point condition. Okay, so we set this, sorry, bubble kan, one sama je, it's okay. So you have to work with temperature more than 129.9. So let's choose 10 degrees higher. So we don't want this to be at saturation temperature, so we go we choose this one to be 140 degrees Celsius because it's a 10 degree higher than the saturation temperature. So because we want to ensure that everything is in vapor phase. Okay, so that's it. That's it. Okay, now let's do this. This is on distillation column. Kita akan pilih methanol. This is the methanol we add, and then another one is production of methanol is carried out in a moderate pressure sensitive loop by direct hydrogenation of carbon dioxide, which generates a liquid product that contains a binary mixture of methanol and water in equal proportion by mole. Okay, now the next one is water lah. So we add there, and then it is equimolar kan. We go to fluid package, and we are going to provide a commercial methanol that is nearly free of water. Dehydration is achieved commonly by distillation. So we are going to separate methanol and water through distillation. The fluid package in here, Pang Robinson. So kita pilih Pang Robinson lagi sekali because that is the user-friendly type. It has a wide range of library in that. Now we go to our environment tool. Then we get our stream. We put in the information in here. Stop me if I am too fast, okay? We go to the composition. Wait, I need to stop my WhatsApp code. It's too busy. Okay, in here. Dia kata equimolar kan. So equimolar is 0.5. Enter. And that's 0.5. Enter. That's 1. This is okay. And then we go to conditions. The feed condition of the process is 2700 kilomole per hour. 2700 kilomole per hour. And then the temperature is 25 degrees Celsius. The pressure is 7.2 bar. Okay. It is then split equally and fed to two distillation columns, one at 7.2 bar and another one at reduced pressure 5.2 bar. Design specification for both distillation column as shown in figure table. The table dah. Okay, now. So yeah, okay, now this is converged. Now we have to split the stream into two because probably the stream is too huge to be handled by one DC. So this is actually the T. We use T. Okay, T ni is actually the split the stream lah. So we have another stream. We go there. So the inlet stream is 1. The outlet stream is 2. And the next one is 3. Okay. Unknown splits. It says here unknown splits. You go to parameter. Then we have a flow ratio. So flow ratio dia kita kata kita bagi dua lah. 0.5 and 0.5. Okay. So total kena 1. The flow ratio is divided according to mass. Now, we are good. We have this. So we need this one to be at 7.2 bar. So we go to our model palette. We find distillation. So this is our distillation column. We bring it here. So we choose energy stream. So in here, we are going to use total condenser for DC. Dekat sini, use split ratio 0.5, use total condenser for both DC, and pressure drop in both DCs must be estimated. So because this is total condenser, means that the fluid from the vapor here, everything will be condensed. So we only need one stream there. And then we are going to need another stream at the reboiler. And then we also require energy stream. This one energy stream, require energy stream for the condenser. We also require another energy stream for the boiler because it needs to supply we need to vaporize the liquid dekat the bottom, and we need to condense the liquid for as the top product. So this is going to be your bottom product, this is going to be your top product. Okay, now, so this is your stream, which is stream 2. Okay, now the condenser energy stream is Q100. The reboiler energy stream, that is a Q101. Then we choose total condenser. So if we choose partial, means that we are going to have two streams up here. Okay, this type of condenser, okay, this type of partial condenser is very, very useful when we have vapor. Okay, vapor dekat stream ni, kita ada vapor. So we do not want trying very hard to condense the vapor components such as hydrogen, oxygen, carbon dioxide, carbon monoxide, because when you condense all that very volatile component which is nitrogen semua tu, you are going the utility of this is going to be very, very high. Means that the temperature can go up to minus 200 something because you are trying very hard to condense the volatile material component lah, the gases tu. Okay, the inert gases tu. Not inert lah, the gases. So might as well just let it be in a vapor phase, and then whatever that is need to be condensed, your product, put it in a liquid phase. But if you are very sure, in this case, this is a case of methanol and water, then we can actually use total condenser because we want to condense your methanol kat sini. Okay, so if you go for full reflux, everything would be in a vapor phase. So kalau you tahu memang gas, you ada, this is a binary component, binary dissolution column. One would be in liquid phase, another one in vapor phase. So you choose full reflux. If you know this is you want the output to be in liquid phase, you choose total. If it's a mixture, especially when you have gases like oxygen, nitrogen semua tu, so you choose partial, so that your requirement of your condenser does not go crazy. Alright, so in this case we are going to choose total because we want to recover. This is only two systems, both are in liquid, so we expect methanol to be up here and water to be down here. So overhead liquid outlet, which is 4. Okay, bottom liquid outlet, which is 5. Okay, you go next. Now, this is the type of heat exchanger that we want to work with. I mean the type of reboiler that we select, does not really matter. So we choose a regular Hysys reboiler. You go to next. Okay, now, this is a very important part where you have to choose what is the pressure across this. Okay, so the pressure across the dissolution column will be decided by what is the pressure at the reboiler and what is the pressure at the condenser. So in here just now it was 7.2 kan, 7.2 bar. So in distillation column, you have to be very careful because you know that the driving force of flow is pressure. There must be a pressure change from high pressure to low pressure. So, and also in here, it produces vapor. Okay, when it produces vapor, you want the vapor to travel upward. Okay, so when you want the vapor to travel outward, means that the pressure at your reboiler must be higher than the pressure of your condenser. But you want the system to be, you want the component to flow inside the distillation column. So this one has to be with the highest pressure, then this is the second highest, and this is going to be the lowest pressure. Then for that, we have to estimate it. So for this case, let's estimate it. The pressure going in is 7.2. We can say I want to make that the change of pressure between 4 and 5 about 1 bar. Okay, so this is 6.2, 7.2. Let's estimate this one to be, I don't know, 6.8, 680 kilopascal. Okay, and this one 580. Okay, now the pressure change that you set in the distillation column will actually affect your product purity. So you can actually manipulate that as well. Okay, now, so if your condenser pressure ni, if you put it higher than this one, there will be something that come out. For example, I letak 700 kPa. It will say warning, a pressure reversal was detected in main tower lah. So the pressure reversal detected means that there's a reverse pressure from condenser to reboiler. Okay, the flow will go like this. So meaning that your vapor cannot travel upward. Your liquid will travel to the bottom of your distillation column through gravitational flow. So it's not an issue. But the biggest issue is now with the vapor. So when this happens, you know that you have set your condenser pressure higher than your pressure daripada your reboiler lah. So that's this one. Let's do this 580 kPa. Also, that kind of notation also can occur if you set your reboiler pressure higher than your inlet. Say for example, you want to do it at 100 kPa. Boleh pula. Well, that is principally wrong. Okay, let's change it to 680. Okay, now we go to next. Oh, before that, we go here because it says the number of stages in DC1 is 12. Okay, you can improve the product purity by increasing your number of stages. The higher your number of stages, your product purity will get better. Okay, and your product purity yang dekat bottom dengan top ni will be depending on how much your customer wants actually the product purity. So you tak boleh jual ikut suka hati you. So for example, methanol in this case, katalah we want it to be at 99%. So you cannot design your distillation column with the product purity at the top ni 80%. Ikut suka you. Siapa yang nak beli kan? Because the customer wants it to be 99%, but you are only managed to produce it at 80%. So that is not right. So how you do this? You increase your number of stages. So we are going to see this later. Now, this one, the inlet stage also you can manipulate it. So in this case, let's set it at stage number 6. The total number of stages is supposed to be 12. This one is supposed to be 6, but tadi dah tukar pula dah. Okay, so the inlet stage is stage 6. The number of stages is 12. Let's go back to the front. Okay, now we are this one is optional, so you don't have to put it in. We will let Hysys to calculate it. So in this case, we are setting the reflux ratio to be 1. Ikut je apa yang Ketan ni cakap. So 1.1. Later we are going to see is there any type of manipulation that we can do to achieve the desired purity that you want. Okay, now reflux ratio is 1, and then the liquid rate in this case is 1000. The distillate 1000 kilomole per hour. From my experience, setting the liquid rate and reflux ratio is more difficult to converge the dissolution column compared to when you set what you want at the top and the bottom. I mean, setting the product purity, you can actually do it. Okay. So we are done with this. So this is what happened. You're going to see this. Now we go to monitor. Monitor. Before that, we forgot to set the delta P. There must be a pressure change in your reboiler and your condenser. So let's set this one to be 10 kPa. Your condenser and your reboiler is simply a heat exchanger, right? So like what we have done before, we set it to be around 10 kPa to 35 kPa, 40 kPa is fine. So most of the time kita buatlah dekat 10 sebab kalau the pressure drop of heat exchanger about 50, that is a large, it's actually a huge heat exchanger. So you can work with 10, 20. This is only based on estimation to make this one run and to make that the calculation nampak logic. Okay. Now we go to monitor. Monitor here on the design dekat tepi ni actually will tell you what you want the dissolution column, what you want Hysys to calculate it to make it is a must. So in this case, kalau you nampak, we have specified reflux ratio is equal to 1.1. It will give the actual calculation value. Now, we tick this because we want to activate this so that Hysys will calculate based on calculation supaya dia dapat reflux ratio to be 1.1. Okay. And they want the distillate to be at 1000 kmol per hour. Now, this is actually a very strange way of setting your distillation column because the most important thing that you want from distillation column is to achieve the product purity at both the top and the bottom, right? So, when this happen, kalau I don't set it this way lah. If I were to have only a separation equipment to separate using distillation column, this is not how I go about it. But because this is only a mula-mula untuk you, so kita try lah this way. Kejap lagi kita akan ada more exercises. Right. So this is fine. Kalau you tengok dekat sini, when you tick the active here, this one the degree of freedom is equals to 0. Which means that it is ready for calculation. If this one is like a parameter, katalah kita take this one out, the degree of freedom is equals to 1. Means that, say for example, this one has 30 calculations, 30 equations, you are only have information for, katalah for example, this one has 30 unknowns, you only have 29 calculations. So you need to have another equation so that all the 30 equations can be solved. So bila you ada 30 parameters, 29 equation, you are lacking of 1 parameters and the degree of freedom is equal to 1. So bila kita tick kita activatekan your distillate rate ni, then the degree of freedom is equal to 0. Nah, dia pun dah buat calculation, it is already converged. So that's it. So let's see the product purity in here. This is supposed to be methanol composition. So the methanol is, when we want to check for product purity, we always look for mass fraction. We don't look for mole fraction. So the product purity in here is only 78%. Okay. And in here water, because this is water, later, ini dekat, okay. Now, this is water. Water yang 99.16%. So this one, maknanya most of your methanol already in here, but also there's a big chunk of water in here. You don't want that. Okay, what you want is that you want a good separation so that you can send the water to the treatment plant. You don't recycle water in the plant. You don't recycle it. This one has to be sent for treatment, and this one achieve the product purity that you want. This is stream 4. Okay, and so that you can sell it. So at this point, that's not achieved. So you have to do something supaya katalah dia achieve 99. So all this water will go dekat bawah ni. Right. Methanol and water is a very simple equipment, dan bila kita very simple component. When we try to separate it, we know that methanol will be at the top, and water to be at the bottom. But how are we going to check? Say, for example, we have two components that we are not familiar with. So how do we know which one at the top and which one at the bottom? Any idea how to do this? Ada tak sesiapa boleh jawab? Anyone? Beritahu dia, boleh jawab tak? Agak-agak. How do you think? How do we decide which one at the top, which one at the bottom?
Based on boiling point.
Yes, correct. Thank you, Taudin. So how you're going to look at which the boiling point of the metals? You go to the properties. Okay, you go to the component list. You pergi dekat methanol ni. You double click here. Then you go to critical. You can see that the boiling point of methanol is at 64.65. Okay, now you go to water. The melting point, normal boiling point for water is 100. So no, you know for the fact that methanol will be at the top and water will be at the bottom. So that's how you decide. Okay. Now, so we leave it like this. Kita assume that this is already a good success because we can converge distillation column. So let's deal with the second stream. So you need to reduce the pressure here to 5.2 bar. So what you need is to install a valve, and then we put in another stream. Then the inlet stream is 3, the outlet stream is 6. Okay, what we don't have, this is unknown delta P. Because the function of valve is to reduce the pressure. Now we put in at the outlet stream the pressure to be at 5.2 bar, 520 kPa. Now we are okay, and the vapor phase fraction is 0. You do not want condensation or evaporation to occur in the valve. It will cause cavitation. So you always have to ensure whatever coming in and coming out from the valve is of the same phase. Okay, in here this is liquid, this is also liquid. So the condensation can also only happen dekat whether it is in equipment, condensation or evaporation, whether it is in equipment or whether it is in your heat exchangers. Okay, it should not happen in your pumps and in your compressors as well. So that is actually the guideline that you have to use lah. Sebab kalau ada liquid in your compressors, you will definitely destroy your compressors. And you also, if there's a vapor in your pump, then you will actually damage your pumps. You don't want that to happen. So you can actually decrease the pressure guna valve, but at the end of the day, you need to check what is the vapor phase fraction dekat sini. Okay. Ada question Ada question ke? Tak ada You all kalau ada question on theory, you have to ask me tau. Because this is the time. Later on next semester, you dah kena buat your design project, then you're going to have problem with it bila everything goes down the drain, salah theory and so on and so forth. Okay. Okay. I told you just now that if we want to separate ammonia and water, the best way to do it is by setting this one at vapor phase fraction. vapor phase fraction equals to 0, maknanya dekat bubble point condition kan. Tapi because we are following this, dia dah suruh tukar kepada 5.2 bar. So kita ikut je cakap dia dulu, later on nanti kita manipulate. Okay, later on. Don't get confused because the purpose of this exercise is just to converge the distillation column. But this is not optimized. So you know, when you have a knowledge in the fundamental of fluid flow and all, the separation, so you can actually apply the knowledge so that you can optimize you punya plan ni. Okay, so we are okay now. Let's do the connection. So we have, this is 6. Now we need total condenser again. So that is 7 and 8. So this is 7. So this is 8. This is Q103. This is Q102. Then the number of stages here is 15. And the tower, you want it to be, the feed inlet to be at the 4th stage. All this will actually affect you punya separation product purity. Now we are okay. We go to the next one. So we just leave it like this. We are going to use reboiler. And then let's decide on the condenser pressure. So coming in here is 5.2. Reboiler pressure, I don't know, 4.6, 460 kPa. And in here is 360. I just estimate. So pressure drop here about 10 kPa. 10 kPa. Benda-benda ni semua bila you buat design project is not given. So you have to estimate, use your common sense. Now reflux ratio in here 1.2. And the liquid rate is at 900 kilomole per hour. Then we are done. Okay, so again, very useful if we check dekat our monitor here. Now both are activate, so we can run this. You can see temperature versus tree position from the top. So daripada dia kira top, bottom nombor 1, the top is the nth number of tree. So this is the dekat dengan reboiler, so that's the highest one. So let's run this, tekan run. So it converges. So the temperature changes lah daripada 110 kepada 150. Kalau you tengok pressure, that's how the pressure changes. Okay, from the bottom 3 to the top 3, from 330 to 460 kPa. So this is the flow process slide. Okay. Okay, so we have actually converged this. Now, let's go to the next one. Monitor the mass fraction. Kalau you tengok dekat soalan, what are the mass flow rate of the feed before entering DC1 and DC2? Okay, we dapatlah jawapan tu. What are the mass composition of methanol and water at bottom and distillate for both DCs? So that's the answers. Monitor the mass composition of water and methanol at bottom and distillate for both DC if the reflux ratios is varied. Explain the variation. Okay, now let's work on this. Kita pilih satu. You can try it later, yeah. So you go to monitor. You can always change it from here. Just now, your punya composition ni. So let's see. We want to see how this varies. Let's change this to mass fraction. Mass fraction. You go up. So now at distillation DC2, your mass fraction is 84%. So let's change the reflux ratio. So let's change to 4 and see what happened. We enter. So your mass fraction, ada tukar tak tadi? 1 point, tadi apa? 1 point, tadi berapa? 1.2 1 point 2, tadi 4 is 0.8417. So if it's 1, 2, tukar sikit lah, 0.8415. So at reflux ratio 1.2, 0.8415. If we change it to 4, it goes to 0.8417. Let's put it as 20, reflux ratio. So the mass fraction change it to 0.8418. So we know that this one can be changed, but there's no use to change it by just to increase the product purity by changing the reflux ratio. Okay, let's change something that is important. Okay, now it says here, kalau question number 5, identify the best design spec for both DC that can achieve 99% methanol. Record the set value. Okay, so as I said just now, what important is what you got in here. So what we want to do, that is the thing that you need to make it activate. How you do it? You add spec. You cari column component fraction. We want the component fraction at the top, okay, to be at 0.99. Dekat 7 kan? Okay, the stage, you go to condenser. Okay, I always do this. You can choose whether you want to do it in the stream. You can put it stream 7 or you do it dekat stages. But I always like to do it dekat stages. I don't know why. So the stages here that I choose is condenser. The flow basis is mass fraction because I nak set I nak the methanol to be 0.99%. So I want it to be in liquid phase. Maknanya condenser kan ada dua kan, satu dekat vapor phase, satu dekat liquid phase. So you can choose any of this, but I would prefer to do it liquid. Then the component in here is methanol, and the spec value mass fraction is 0.99 because I want to sell 99% of my methanol to my customer. So sekejap. Oh, tak masuk pula. Component fraction. Okay, ni. Ni 0.99. 0.99. Enter. Kena enter. I always forgot to enter this. Now, instead of you are setting the reflux ratio to be 20 ni, we can actually estimate it. Okay. And katalah for example you really want the distillate rate ni dekat 900. Okay. So what you do is that you just take this one. This is what you want. You don't care. Macam I don't care what's my distillate rate. Tapi I just want my composition to be 99%. And then my degree of freedom become -1. Maksudnya dia dah overspec. So I just take out one of those. Maknanya my reflux ratio will be estimated. And it do the calculation now. Dia lambat sikit sebab I punya reflux ratio ni. Dia try to estimate it to be close to this. Let's stop this. Along the way, if you think that the calculation takes a long time, you can actually change it back. I don't know. Okay, run. Okay, dia tak solve juga. What we do, we stop this. Okay, now we know that we can actually change our stages. Let's change this to 30. Enter, you go to monitor, you run. Tengok, dia improve tak? Okay, now the current value is at 0.9701. We want to achieve 0.99 of methanol at the top. So this is still struggling. They're still struggling calculating it. So you stop. So I akan tambah lagi my number of stages. Let's do this 50. And run. So they close. Okay, it's close. Now, the issue now, because kita letak our distillate rate to be 900, and the current value now is 698. So let's stop this one. Do we really care for the distillate rate to be 900 km per hour? Kalau you tanya ke I don't care. So because what I want is I achieve I punya component fraction dekat top dengan bottom tu. Okay, dekat top dengan bottom tu kita achieve. So let's not make this one to be an active punya condition. We make this one as estimate sebab the calculation yang ini. Okay, now we want the water to be at 99% dekat bottom. Okay, this one at the top kan. So let's expect at the end of the day that's what we want pun, to achieve the product purity that we want. So let's do this. We go to stage, we go to reboiler. Okay, this is mass fraction. Then reboiler, you change it to vapor phase, and the component you choose water, and you want to force it so that the fraction of water at the bottom to be at 99%. Okay, now we make this active. Okay, now degree of freedom -1. We inactive this one so that it can just estimate. Okay, apa-apa dia dah run dah. Tengok, dia dapat 1 actually. Okay, let's stop this. Let's make this 0.9999. Run. Okay, let's stop this. Go to connection. Kita cuba increase this one 60. Go to monitor. We run this. The fixed current value at 20 here, that's the problem. Nak capai dah ni. Okay, let's stop this. This is very, very high already. Let's make this one, I don't know, 28, 25. Let's see whether there'll be any changes in that. Converge. Okay, so means that you can actually manipulate your inlet stages, your number of stages. You can reduce it now and see if we can reduce number of stages, because when you reduce number of stages means that the cost of your DC would be less. So the value that we estimate here is based on 100% efficiency. 100% rate efficiency means that this is ideal type of distillation column. In real life, when you are trying to simulate, when you are trying to design the distillation column, you have to divide by the efficiency of the DC, so that the number of the stages that you got from here, you divide by the efficiency, which is, say for example, 50%. So the actual number of stage would be 120. Katalah the efficiency of this one is 50% kan. So the theoretical number of stage 60. So 60 divided by 0.5 lah. So the actual one is 120. So 120 is fine. It's not an issue. So in this case, you know that you can change this. You can change the number of stages. But I was just about to change my pressure drop tadi. Pressure reboiler dengan condenser. So it will actually impact you punya product purity to actually, but this is converged, so this is fine. So in here you dapatlah methanol you 0.99. You can actually do. So if your customer wants it to be 0.9, customer wants it to be 99.9%. So that's how you do it now. Okay. So kalau nak buat yang dekat atas ni pun you can do the same lah. You manipulate it. So dekat sini I dah tulis semua kot. I mean dekat I've shown you what's the reflux ratio and how. Well, okay. So that's it lah kot. Dah 12.52 pun.